Yeah, so I'll be talking about snowlines and externally photoevaporated protoplanetary disks. That's my shorter title. The previous speaker gave a really nice introduction to what I'm going to be talking about, and I thank her for that. How do I? Sorry. Hey. Oh, there you go. Sorry. To motivate my talk, basically, I've listed here a couple of like the water content by weight of some of the bodies in our solar system, and you can kind of see that they really vary from about like say 0.1% to about tens of percent, and in possible exosolar planetary, water worlds, you could probably have like up to 50% of water by weight. So what really decides the water content of terrestrial planets? To get into this question, we're talking about snowlines. The last speaker again introduced this. So a snowline is basically the region that kind of demarcates where water condenses as ice and where it doesn't. So you can kind of see a snowline on a mountain here, and but in a protoplanetary disk, water sublimates at 170 Kelvin, and so this was initially thought to exist at like 2.7 AU from the sun, and so here shown as here. So it was theorized that bodies that formed within this snowline would be water dry, and the bodies that formed outside of it would be water rich. And subsequently, a lot of more like detailed protoplanetary disk models that kind of assume more accurate dust properties and temperature profiles in this kind of came to the conclusion that this snowline need not necessarily be at this value. It could be much more closer in, even as close as 1 AU. And also, subsequently, models found that like temperature is probably not the only criterion, but radial transport of volatiles across the snowline also matters. So probably this picture of the snowline is not as static and clear as this, but probably something a little bit more murky. What do I mean by radial transport of volatiles? There could be like different types of like volatile processes happening across the snowline. You could have a continuous outward diffusion of vapor outside the snowline, and then you could have like an inward drift of icy particles, which kind of orbit at a different frequency, at a different frequency than the pressure-supported gas, and because of which they would like spiral inwards. And upon reaching the snowline, they would melt and so you would have like a cyclical like transport of water vapor outside and inside the snowline. And to this scenario, if we were to add the process of external photoevaporation, then it could be a little bit more complicated. So what external photoevaporation is that the sun was born in a massive. It's very likely that the sun was born in a massive star-forming region, and its disk was sort of intensely irradiated by radiation from nearby massive stars. So if that was the case, then it could frustrate this inward drift and kind of enhance an outward volatile transport outside from the outer edge of the disk. So we kind of consider this process as well in our modeling of disk structure. So what this project is about is basically radial transport of volatiles would be sort of intimately connected to the disk structure of the protoplanetary disk, and we kind of probe the disk structure a little bit more. So to very simply represent density structure in a disk, you kind of like call it by a radial power law with an exponent of p, or here. And this density structure would be like very intimately connected with the temperature in the disk. So if you represent that as well as a power law with Q, we go back to a result by like Tokechi and Lin, who say that if the sum of these two exponents is greater than 2, then the net Wöhler transport is likely to be outward, and we kind of test what this is really likely to be. So if you assume like a standard value of the temperature power law, with a Q of 0.5, so we are like left to determine what is P. And the previous speaker again spoke about the minimum mass solar nebula model, where each of the giant planets is kind of like smeared in their current annuli, and you can infer a surface density profile with a slope of 1.5 with such a model, which is shown here. Later, Desch 2007 kind of included the positions of the giant planets from the Nice model, and he found a slope that was more steeper for the surface density profile. He basically thought that, okay, the Nice model positions of giant planets is a more reasonable assumption to make, because a lot of migration of the planets like followed after hundreds of millions of years. So basically in this project we model the structure and evolution, and try to see what affects the structure, how photoevaporation affects the structure, and also we consider a non-uniform alpha viscosity, which I'll be explaining. So we take into account the standard equations of disk evolution by Linden, Bell, and Pringle, where this equation talks about the evolution of the surface density and the rate of mass flow. And we also assume like the standard viscosity parameterization, where nu is given as alpha times sound speed squared divided by orbital frequency. And so most disk models just assume an invariable alpha. Alpha is the same throughout the disk with height and with radius, and it's also the same with time. But we kind of derive this alpha from magnetorotational instabilities, and kind of find that it varies quite a bit, and this has to be considered in disk evolution models. So magnetorotational instabilities, simply put, is like a fluid instability that occurs in accretion disks. It occurs only if if the region in the disk is like sufficiently ionized. And so for this, we calculate the ionization state at each region in the disk. So we consider ionizations by X-rays and cosmic rays, and we consider recombinations of these ionic species and electrons in the gas phase as well as dust grain surfaces. I could talk about more details later. So what we do then is we consider the treatment of Bienstone 2011, where we basically determine the alpha at each region in the disk from the ionization state. And we find that on incorporating these equations in our disk model, that alpha does really change a lot, like over 4 orders of magnitude throughout the radius of the disk, from about like say or less than 0.5. 0.5 is the floor here. I'm sorry, 10 to the minus 5, and to 0.1 in the outer regions of the disk. And it also changes sort of dramatically with time. And finally, we also include photoevaporation using the treatment and the results of photodissociation models from Adams et al., where they basically the mass loss rates due to photoevaporation mainly depend on the disk radius at on the disk radius, as well as G naught, which is kind of like the parameter for describing the radiation intensity that the disk finds itself in. So here we use a value of a G naught of 1,000 to be we consider that to be typical of what disks are likely to phase in like rich star forming regions. And finally, to go to our results, so I'm showing you the first sort of a viscously evolving disk case. And to kind of describe this graph a little bit, this is the surface density on a log-log plot with the radius. So the radius goes from 0.1 AU to 100 AU here. And each of these, so this is the initial, the dotted line or the dashed line is the initial profile of the disk, and each of these lines are solid lines at each subsequent year, million year of evolution, from 1 million years to 10 million years. So you can see that the disk obviously becomes less massive with time, and you can also see it sort of expand outwards. That's what a viscously evolving disk, without any of the effects that I described above, would kind of react. So after 10 million years of evolution, only like half of the disk remains, and you could kind of like keep in mind this number as I show you the different cases. So so the other thing we do is we also track the slope of the surface density profile between 5 and 30 AU, and here we find that the slope P is about 1. So next we go to a photoevaporated case. So it's basically a viscously evolving disk without MRI alpha with photoevaporation. And you can see that the slope that we keep track of between 5 and 30 AU, it's slightly steeper right now. And the disk is less massive even more. Only 5% of the disk remains after 10 million years of evolution. And it's also truncated to about 50 AU. The other interesting thing that you can find in this type of disk is the behavior of the transition radius. So in a viscously evolving disk, this transition radius usually moves outward with time, and we find that this radius, which is basically the radius where the net mass flow changes from inward accretional flow to outward, this moves inward with time, and in this disk, it actually moves as close as 17 AU. From the start. So basically what this means is that mass as close as 17 AU is drawn outwards from the outer edge of the disk. Then we take the third case where we include MRI alpha and photoevaporation, and we find that the disk rapidly dissipates within just 7.5 million years of evolution. So what happens is the slope becomes really, really steep, and most of the disk is just gone within 7.5 million years. And but when we include dust in this scenario, the previous case did not have any dust in it. It kind of has has a totally opposite effect from what we just saw. What we see here is the dust kind of stalls the inner disk evolution by sort of absorbing charges in the interior of the disk, and the rest of the disk just piles on top of the inner disk, kind of erecting this really steep profile, where P is like much greater than 3. And so this is kind of really interesting. Of course, we don't include grain growth here, so that is an important caveat. So conclusions, photoevaporation does cause steep profiles, so we get a large P, and this is likely to create like more outward transport from the result by Takeichi and Lin. MRI alpha is very sensitive to the presence of dust, and dust causes the stalled evolution of the inner disk. It doesn't let it evolve. Disk dispersal would require grain growth, which we don't model here. And the transition radius moves in, so the gas is removed from the inner disk, and in this previous case, it moves as close as 3 AU, which is why it's very important for the terrestrial planet region point of view. So dehydration of the inner disk, especially is important, especially for disk-enriched clusters. So thank you.
Time for one quick question.
Huh? So Have you done a sensitivity study to see if you turn off the MRI alpha and just include the dust, if it essentially reproduces the same shape? Does it just completely overwhelm the alpha variability?
No, actually, we have not performed such a case.
Okay.
Yeah. Yeah,
That would be interesting to see.
I guess so, yeah.
All right, let's thank the speaker one more time.